Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are, of course, going to start with the study of chapter 5, which deals with the study of the three-dimensional structures of organic molecules that we refer to as stereochemistry. Okay, Valerie, can you go ahead and read for us what we are going to be discussing today?
Stereochemistry, what is stereochemistry, Stereochemistry, Chirality, and Enantiomers, metal compounds, resolution of isomic mixtures, optical activity, and stereochemistry reaction.
Okay, thank you. So today we are going to begin a discussion of stereochemistry. Of course, stereochemistry is a very important area of chemistry. For this area of chemistry, we will be discussing the three-dimensional structures of organic molecules. In so doing, we will expand our knowledge on of isomers, different types of isomers. We will discuss chirality and enantiomers. There are stereomers, meso compounds, and then we are going to show you how to use stereochemistry to resolve mixture of organic compounds. We also discuss optical activity of stereoisomers, and finally we will show you how to use stereochemistry in organic reactions. Okay, before we go into our discussion, I do want to let you know that the exam result is out. I will give you back your exam at the end of today's session. So please stop me 5 minutes before the end of class so I could give you back your exam. Also, the next homework assignment will be the end of chapter questions of chapter 5 in OWL, and that will be due on Sunday, September 30. Sunday, September 30. Okay. So I also want to let you know that the next exam, of course, will be almost a month from now, which is October 18. Okay, on this slide, of course, we give you a series of learning outcome objectives. And I'm going to leave you to come back to this slide. Which will guide you with regard to your study of this chapter. Some of these concepts are the concepts that we will be testing for all of the quizzes and exams that we are going to give you. So I will leave this for you to go over some of these concepts. These are very, very important concepts indeed. Okay. Again, at this point, the question is, what is stereochemistry? Does anybody have an idea what stereochemistry is? Yes, go ahead. Yes. Yes. Go ahead. Yes, thank you. So that is stereochemistry. In other words, we are going to study the spatial relationship of the atoms or group of atoms in a given molecule. another way to put that definition is to say that this stereochemistry is the study of the three-dimensional structures of molecules. You take a look at this molecule here. What we are showing you with regard to this carbon here, we are showing you the three-dimensional nature of all of the groups that are attached to that carbon atom. So those are the kind of concepts and, of course, skills that we are going to be discussing during the course of this semester. We will be taking a look at molecules and look at the spatial orientation of all of the atoms within that given molecule. Now, some of you may ask, why is stereochemistry important? For those of you going to biochemistry, stereochemistry is very important. For those of you going to the pharmaceutical industry, stereochemistry is very important. If, for example, you take a look at this molecule here, D-glucose, most of the physiology of our body depends on the use of this D-glucose for the generation of energy. This is a particular stereoisomer. The other isomer of this, L-glucose, the body does not use. In other words, our body knows how to recognize a particular stereoisomer in performing a lot of metabolic transformation. So stereochemistry is very important indeed. And of course, for those of you going to the pharmaceutical industry, you will also find that a lot of drugs actually are those that depend on the stereochemical relationship within the atoms of that given molecule as they relate to their activity in our body. So anyway, so stereochemistry is very important indeed. Now what I want to show you here, take a look at this table, just to show you at the extent to which the field of stereochemistry is fairly well defined. We already know constitutional isomers based on what we did in chapters 3 and 4. Now what this table shows you is a series of isomers. You start with your isomers, and if I ask you what are isomers, what are isomers? Isomers are different compounds with the same molecular formula, right? Those are isomers, different compounds with the same molecular formula. So that we know from chapters 3 and chapter 4. With same molecular formula. So now we have isomers, and then from isomers we also know we have constitutional isomers. So what are constitutional isomers based on what we did in chapter 3 and 4? What are isomers? Anybody? Of course, isomers, yes, go ahead. Compounds with the same molecular formula but different arrangement of the atoms, exactly. So constitutional isomers are those compounds with the same molecular formula, of course because they are isomers. The difference between them is that the attachment of the atoms or the arrangement of the atoms are different. So that is what we did in chapter 3 and 4. Now we are going to now introduce you. All right. We are now going to introduce you to a different set of isomers that we refer to as stereoisomers. Now, stereoisomers are compounds with same molecular formula, right? Same molecular formula, comma, same attachment of atoms or same arrangement of atoms, same attachment of atoms, comma, but different orientation of the atoms in space. But different orientation of the atoms in space. Yes. Stereoisomers. These are what I'm doing here, defining stereoisomers. Okay. So this will be different molecules that have the same molecular formula. They have the same arrangement of atoms or attachment of atoms. The only difference between them is the orientation of the atoms in space. So we are going to give you examples of this as we go along during today's session. Now, under stereoisomers, you also have another series of isomers. We have what we call diastereomers. We'll define those later. We have enantiomers. In the case of the enantiomers, these are mirror images that do not superimpose on each other. Then we have what we call configurational diastereomers. And finally, we have what we call cis-trans diastereomers. At the end of this chapter, you should be able to take a formula. Okay, let me take this formula out. I don't want you to use this. You should be able to take any kind of formula. For example, this kind of formula here, CH16. You should be able to take any kind of formula like this and give an example of each one of these type of isomers using this formula here, or using any formula. In other words, if you have in an exam in which we give you a formula and say, give an example of each one of these isomers using this formula. So you should be able to do that at the end of this presentation. Now, before we go further in our discussion of stereochemistry, what I want to do now is to show you how to represent organic molecules using three-dimensional structures and also sometimes using two-dimensional structures. Because this is very important in our understanding of stereoisomers. Yes, go ahead.
I'm sorry, you said it already, but I just want to reiterate. The difference between resonance and isomers is that isomers is different configuration and resonance is different
No, resonance has nothing to do with isomers. When you write resonance, you are dealing with the same molecule, the same compound. When we go along, I will give you example I will give you example of what we have there in terms of the different types of isomers. But keep in mind that isomers are different molecules that have different compounds that have the same molecular formula. Okay? Okay. So now let us show you how to represent organic molecules in 3 dimensions. So we're going to say 3-dimensional representation of organic compounds. Take a look at this molecule here. For the purpose of this discussion, this group here, right here, this is a methyl group. Think of this as a methyl group. Also think of this here as a methyl group. This here is your hydrogen. This here is your chlorine. Okay? This is your carbon. So what are we showing here? We are showing stereochemistry for this molecule, in which we show the direction of all of the atoms in space, the spatial orientation of all of the atoms. Now, if you take a look at this molecule from where you are, tell me what atom is to your right? Hydrogen. What atom is to your left? Chlorine. Those two, the hydrogen and the chlorine, where are they going? They're coming towards you, right? Okay, they're coming towards you. Now, what you find, this is an sp3 carbon atoms. For the most part, we are going to be dealing with sp3 carbon atoms. And therefore, the stereochemistry around an sp3 carbon atom is what we call a tetrahedron, which means that this carbon is sitting in the middle of a tetrahedron. Now, if you look at this hydrogen coming at you, chlorine coming at you, when that happens in an horizontal orientation, what happens, the other 2 bonds attached to this carbon, where do they go? They're going away from you in a vertical orientation. That is the nature of tetrahedron geometry. So whenever you see 2 groups coming at you, the 2 other groups will be going away from you. Okay? If those 2 groups you are looking at, if they are in the horizontal position, the other 2 groups will be in the vertical position. This is very important. Okay? Now, so let me now write this. Okay? From your perspective, so I'm going to write this. I'm going to assume that I'm sitting where you are. So therefore, you say that hydrogen is to my right, right? So I have carbon is here. So if you say hydrogen is to my right, I will do this. Because the hydrogen is coming at me, I will use what we call a wedge. And then the chlorine is also coming at you, I will use another wedge. Okay, the wedge means that those 2 groups are coming at you. Now, the methyl group, where are they going? Going away from you. So how do I represent those? I do this. This is what we call the wedge and dotted line convention. And dotted line representation. Okay, in which we have, I will say the hydrogen is to my right, and of course the chlorine is to my left, based on where you are sitting. Now we want to look at the same molecule. Keep in mind, this molecule is not going to change, but your position will change, the way you look at the molecule will change. Supposing you look at the molecule this way. Notice that this molecule has not changed. Okay? Now let us now give a three-dimensional representation of that molecule again. Okay, the chlorine, what is the chlorine doing? Coming at you, right? What is the hydrogen doing? It's not going away from you, right? That molecule did not change. What has changed is your orientation, your position. Now, the methyl group are now on the plane of the paper or the plane of the board, depending on what we are writing with. Okay, so now, based on your perspective, if I want to write this structure, okay, the hydrogen is going away from you, right? I'm sorry, the chlorine is coming at you, so I'm going to write it this way. So we have carbon here, and the chlorine is coming at you. Let's do this. And the hydrogen is going away from you, right? And the two methyl groups are on the plane of the paper. So the regular line tells you which bond is on the plane of the paper. Now, what have we done now? These two molecules here. Ordinarily, if I give you these two molecules, if I ask you, are these molecules the same? If I ask you, are these molecules the same? Because they look different. The only way to tell whether these molecules are the same or not is to give the name of these two molecules, the way they are rated. Okay? But these are the same. Based on what we just did, yes. No, it doesn't matter. As long as it's a wedge, the wedge is always coming at you, and the dotted line is going away from you. The regular line is the bond on the plane. So keep that in mind. This is very important. Okay? As we just told you, the regular line, if I have this line, that means on the plane. Okay, the regular line is on the plane. So that means this here is on the plane. Look at what we have here. You see, what you are doing is representing what you see. Okay, this is the plane right here. This is coming at you. This is hydrogen going away from you. And this methyl group on the plane. Okay? Okay. So now we have the wedge and the dotted line representation. Yes.
So by doing this to the molecule, what are we trying
to do what? Well, I'm trying to show you how you represent molecules in 3 dimensions.
Oh,
Okay. Okay, that's why we say 3-dimensional representation of organic molecules. Because since we are going to be dealing with stereochemistry, we need to know how to represent these molecules in 3 dimensions. Okay. Now, another convention that we use to represent stereochemistry in organic chemistry is what we call the Fischer representation. This is very important. Remember the molecule I gave you earlier? This here, we have the chlorine here, and then we have the hydrogen here, and then we have the methyl here, and then another methyl here on the plane. Okay. Bring that molecule back. This is right here. Supposing now we have this molecule right like this. What we want to do here, the Fisher representation is actually a two-dimensional representation of a two-dimensional structure representing a three-dimensional molecule. Now, what does that mean? Because you are looking here, right? Supposing I flatten this out. Imagine that I flatten this horizontal group out, the chlorine and the hydrogen, right? The hydrogen is on your right, the chlorine is on your left. Okay? If I do that, I could turn this to this, in which I now have hydrogen is to your right, right? Okay, so we have hydrogen here, and chlorine is to your left, chlorine here. If I also flatten this out, okay, what will be on top of you? Okay, that is why I brought this guy here. See my friend? You see what is looking at? What is on top of him? The methyl, and what is below him? Methyl, exactly. We're going to be using this a lot. Okay, so what do we have? So what have I done here? What I've done here is to use a two-dimensional structure to represent a three-dimensional, a three-dimensional molecule. And what does this mean? This is what we call the Fisher representation. In the Fisher representation, the horizontal group, what? Just a minute. Okay, she says I should explain the Fisher projection, right? Yeah, that's what I want to do now. Okay, in the Fisher projection, the horizontal group are coming at you. Because that's what we did. The horizontal, when you write the Fisher projection, this horizontal group, in other words, when you write this chlorine and this hydrogen, you assume they are coming at you, even though you are simply using a two-dimensional representation. Is that clear? Now, what that also then means is that the vertical group, the group in the vertical position, in this case, this methyl and this methyl, they are what? What are they doing? They're going away from you. Okay, so the vertical group are going away . Okay, did I explain? Is that what you are asking me? Okay. This is very important because as we go forward in the study of stereochemistry, this is most important. Yes.
So on the drawing on your left, the hydrogen is going away, and then the chlorine, the methyl groups are playing on the plane. So on the right side, they're saying that the methyl groups are going away from you. So I don't know, like, how do you get the left, the picture on the right doesn't make sense to me.
Okay. Look at what we gave you. The left, let me see here. Okay. This is what you told me when we wrote the this here. See, this was going on. Okay. This is what I gave you. This here. Okay, and that is the one on the left. Right here. Okay, this is the way you are looking at this molecule. Okay, in this case, the chlorine is coming at you. Okay, hydrogen is going away from you. That is the way you are looking at this molecule at this point. Okay, now that is a three-dimensional representation, just as we've seen here. Now, what I'm telling you now, another way in which you can represent this molecule is using a Fisher projection. And what do you do to do that? In this case, you could look at the molecule in which two groups must be coming at you in an horizontal position. You have to position yourself so that two groups will be coming at you. Okay? Whenever you want to draw a Fisher projection, take a look at that molecule, focus your attention on the central carbon. Two groups must be coming at you right here. Okay, it's the same molecule, it's just that you are looking at it from a different angle. And that is what we've done here. We simply say, okay, this here, we flatten this out. That's what we've done here. That's what we've done here. And then we flatten this out. And that's what we've done here. Okay, it's still the same molecule. It's just that you are looking at the molecule from a different angle. It's almost as though I'm looking at you direct as opposed to looking at you from the side. I could draw a different representation, but it is the same you. You have not changed. What changed is my position at looking at you. Okay? So anyway, so now the Fisher projection is a very important way to represent organic molecule in 3 dimensions. What is good about the Fisher projection, it is a 2-dimensional structure that represents a 3-dimensional molecule. That is what is good about it, and I'll tell you why that is good in a few before we finish today. Okay, so now we've shown you the wedge and the dotted line representation. Then we've also shown you the Fisher projection. So now let us now start our study of stereochemistry. Okay, take a look at these 2 molecules here. Let me write. Take a look at these 2 molecules. Look at it. What do they think what are they? What do they represent to you? They are mirror images, right? Everybody agree? They are mirror images, right? Okay. Let me do this. I want to see whether I could superimpose this molecule on each other. When I say superimpose, position them so that all of the groups will be in the same direction, right? Let's just see here. Can I do it? Yes. Do they superimpose? Yes. They superimpose. You see? Therefore, those 2 molecules, are they the same molecule or what? They are the same molecule. Even though we showed you they look different, but as long as you can superimpose them, they are the same molecule. Okay? So in this case, keep in mind we say this is green is chlorine, and this is methyl, and this is hydrogen. So let us draw that. So I'm going to draw a Fisher projection of this molecule from my perspective, okay, where I am looking here. So I want to draw the Fisher projection. So this is a CH3 here attached to carbon attached to a CH3 from my position in the vertical position, right? And then to my right you have the hydrogen, and to my left you have the chlorine. Now, if I draw the feature, the mirror image of this, the mirror image will look like this. That is the mirror image. And we both agree that we could superimpose these two molecules. If we simply take this here, if I turn this 180 degrees in the feature projection, if I turn this 180 degrees, right, and then slide it to here, it will superimpose. You all agree? Okay? So this will superimpose. Mirror images will superimpose. Therefore, they are same molecule or same compound. Okay? We all agree on that. Now, let me now give you another example. In this molecule here, this is carbon. The brown is the bromine. White is hydrogen. The red with this here, think of it as the hydroxy group, OH group, okay? And of course, this is our methyl, okay? What is the relationship between these two? They are mirror images. You notice the attachment, they have the same molecular formula, right? So therefore, they must be isomers. They also have the same attachment or arrangement of atoms. So therefore, they must be what? Stereoisomers. Now, whether they are stereoisomers or not depends on whether these two will superimpose. Okay? Let us see. Whatever you do, I guarantee you cannot superimpose this, no matter what you do. I will pass this around if you want to try it. No matter what you do, these two will not superimpose. Yes? So these two molecules, therefore, we refer to as enantiomers. Okay? So we call these two molecules enantiomers. So therefore, what do we call enantiomers? Enantiomers are mirror images that do not superimpose. Yes? No, we get back to that. We get to that. The question is only enantiomers show chirality, but we'll get back to that shortly. Okay, so these two molecules, therefore, they are mirror images, but because they do not superimpose, we say that we call them enantiomers. So let me now write these two molecules here. Okay, I want to take a look at this molecule. Keep in mind, I want to use a Fisher projection. Okay, I want to use Fisher projection. Okay, so I say that. Let me see. Well, I could say this molecule. I am looking here. Bromine is on my right. I'm looking right here. Bromine is on my right. Hydrogen to my left. Hydroxy on top, right? And what is below? Methyl. Think of it this way. This guy is looking, right? Okay. So now let me write it. So that is carbon in the center. Hydroxy here. Methyl here. Bromine, we say to my right. And hydrogen to my left. And then we write a mirror image of this. We draw the mirror image. The mirror image will look like this. Bromine here, hydroxy here, hydrogen here, and methyl here. These are two mirror images that will not superimpose because they just will not superimpose no matter what you do. Okay? These are two mirror images that will not superimpose on each other are referred to as enantiomers, are called enantiomers. They are called enantiomers, yes.
So if you don't have a model, how can you tell that they don't superimpose? Is it because they have each, there's 4 different groups?
No? Okay, very good. Good question. If you don't have a model, how do you know whether they do not superimpose? This is what you do. That's why I told you, pay attention to the Fisher projection. Okay? So once you write the molecule in the Fisher projection, see whether you can superimpose them. You could slide this to here. Would they superimpose on top? Would they line up? No. You could turn the molecule 180 degrees. Would they line up? No. The only thing you cannot do, keep this in mind, you cannot lift the molecule in a Fisher projection from the surface of the paper. You cannot do this. No, you cannot do that. But what you could do, you could do this, okay, which is a 180 rotation, right? 180 degrees, and then slide to see whether they superimpose, or you could simply slide to see whether they superimpose. Those two things you could do, okay? That is the only way you could find out whether they superimpose or not. Yes?
So basically, it really depends on where the atoms have attached on that molecule. Because if the bromine is on the other side, where the hydrogen is, you could superimpose it. So it just basically depends on where.
But bromine is not on the other side.
I'm saying.
No, but the point is, bromine is not on the other side. These are mirror images. Okay? This here is a mirror image of this. But it's not on the other side. Okay. Bromine, you try to make up something else. But bromine is not on the other side. So don't let us keep saying that. So these two mirror images is almost your two hands, right? Can you superimpose your? No. Then it's almost as you telling me, what if my tongue, this tongue there, is on this side? It's not, right? So you cannot superimpose them. This and this are mirror images. If these are molecules, we will call them enantiomers. Your left hand and your right. Okay. So therefore, we call this enantiomers. Now, another thing that you will be able to, that will also help you, anytime you have a carbon atom is attached to 4 different atoms or 4 different groups, that carbon atom is called a chirality center. For example, this here. This carbon here is called a chirality center or chirality carbon. Okay, in some books will refer to this as stereogenic center. Some books will call this stereogenic center. So that is a stereogenic center or a chirality center is that carbon or atom that is attached to how many different groups? 4 different atoms or 4 different groups. If you only have one chirality center in a molecule, that molecule will not superimpose on its mirror image. Okay? If you only have one chirality center or chirality carbon in a molecule, that molecule will not superimpose on its mirror image. Okay? In other words, that molecule will be an enantiomer of its mirror image. Okay, so let me write it. If you have only one chirality center or carbon in a molecule, comma, that molecule will be an enantiomer of its mirror image, and vice versa. That molecule will be an enantiomer of its mirror image. For example, if I give you this here, supposing I give you this molecule, okay, how many chirality centers does this molecule have? How many? 1. It has only one chirality center. Because it's only one carbon in this molecule that is attached to 4 different atoms or groups. Okay? So it has only one chirality center. So therefore, this type of molecule will not superimpose on its mirror image. Okay? So this, and therefore we call this type of molecule a chiral molecule. A chiral. In other words, molecules that do not superimpose on their mirror images are called chiral molecules. Okay? Let me write that again. Molecules that do not superimpose on their mirror images are called chiral molecules. Now the question now comes, if we say these 2 molecules here, if we say these are these different molecules, right? Because they do not superimpose on each other. If we say these are different molecules, how are we going to call them? What kind of name are we going to give them? Huh? What name? Okay. Okay, let me give you an example. Let me give you an example. Supposing you have this. Supposing you have this here. By the way, notice that most of the attention when we deal with stereochemistry, we are dealing with molecules that have chiral centers or chiral carbons. Okay? Supposing I have this. Based on what we've done so far, can anybody give me the name of this compound? Yes. What is the name of this compound? 2-chloro. 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 Why hydrobutane? 2-chlorobutane, exactly. We just did that, right? Okay, so that is 2-chlorobutane, right? Okay, good. Supposing I draw the mirror image. Let us draw the mirror image of that molecule. What is the name of this mirror image? We already agreed that these are different molecules because they will not superimpose. They are enantiomers. So essentially they are different molecules, different compounds. So what are we going to call this? It's 2-chlorobutane, right? Exactly, okay. So we say 2-chlorobutane. So then how do we know which 2-chlorobutane are we dealing with? Right? So now that takes us to the nomenclature of stereoisomers. Okay, so now let us now take a look at the nomenclature. So we're going to put question mark here. Question mark here. Okay. What time do we have, by the way? Oh, 20. Okay, thank you. Okay. So, that takes us to nomenclature of stereoisomers. In the nomenclature of stereoisomer, we determine what we call the absolute configuration. Okay, we determine the absolute configuration of the chirality center of the now by absolute configuration we mean the spatial arrangement. Okay, absolute configuration means equals to the spatial arrangement, the spatial orientation of the groups or atoms of the groups or atom bonded to the chirality center. Bonded to the chirality center. That is what we mean by absolute configuration. So how do we do this? Okay. To do this, we use what we call the Kahn-Ingold Philog sequence of nomenclature in the Kahn-Ingold Philog sequence of nomenclature. If I have this, here I have this carbon here. Okay, keep in mind we are dealing with chirality centers here. Okay. If I have that, what do? We start off by assigning priority to all of the atoms or groups that are attached to the chirality center using atomic number. Assign priority using atomic number. I know your book uses the priority. Your book uses 1, 2, 3, 4. I prefer to say A, B, C, D. A meaning has priority over B, and B has priority over C. So in that case, if we want to assign priority to the groups or atoms attached to this carbon here, which would be priority A? Which is priority A? Huh? Based on atomic number. The higher the atomic number, bromine, exactly. So we say this is 1. I'm sorry, this is A. That's priority A. What would be priority B? Chlorine. Okay, B. What would be priority C? Carbon, right? Carbon has priority over hydrogen. Because carbon has atomic number of what? 12. Okay, so therefore, the C is carbon, and then the last priority here is hydrogen. So we say this is D. Now, according to this sequence rule, let me take this out. To name this compound, you make a motion. You make a motion from priority A, you go to priority B, and then you go to priority C. Ignore priority D. Completely ignore it. Okay? So that motion becomes A to B to C. Huh? Yes. Well, that's the convention. Okay, that convention was established by IUPAC. Ignore D. Okay? You make a motion starting from A, you go through B to C. Ignore group D. Okay? If that motion is clockwise, then you say this molecule has an R configuration. This is R. This here equals to R configuration. In other words, the absolute configuration of this carbon here is R. Okay? Now, if I then draw the mirror image of this, okay, by the way, okay, let us just do that. So what would be the name of this compound, therefore? So what would be the name of this compound? Let us complete that. The name becomes R in paren 2 bromo, no, I'm sorry, that 1 bromo, 1 chloro, what? What's the base name? Ethane, exactly. R, 1 bromo, one chloro, ethane, because ethane is the base name. Keep in mind you follow all of the rules that we've shown you earlier. The difference now, you place an R in front of that name, meaning that it has an absolute configuration of R. So let us draw the S, the mirror image. The mirror image will look like this. Hydrogen here, carbon here, chlorine here, bromine here, and metal here. That is the mirror image. Okay, if we now make our motion, let us make the assignment again. Assignment, we say B, bromine is A, right? Priority A. Chlorine is B. And metal, this carbon is C. And hydrogen is D. Okay, so once again we make our motion, right? We make a motion from A to B, ignore group D, to C. Okay, this is counterclockwise, right? And that is S. The clockwise is R, clockwise motion, and the counterclockwise is S. So therefore, what would be the name of the enantiomer of this molecule? Exactly. So the name becomes S in paren 1 bromo, 1 chloro, ethane. Okay? So in this case, whenever you have one enantiomer has one absolute configuration, the other enantiomer will have the opposite configuration. You only have two choices, R or S. Now, the example I'm giving you here shows you a case in which you have the group of lowest priority, which is hydrogen, is going away from you. That is what the convention says. Before you make your motion, the group of lowest priority must be going away from you. Okay? Your book does it differently, so follow what I want to tell you now. If it just so happens that the group of lowest priority is not going away from you, I will tell you exactly what to do. But before we do that, let us go back and name those two molecules that we gave you earlier. Okay. So what will be the name of these two molecules, therefore? We already know the base name, yes. Okay, so let us assign priority to them, right? Okay, let's start with this. Priority A. This is A. Okay, because of chlorine has a greater atomic number than carbon or hydrogen. Okay? Now, what is priority B between the ethyl and the methyl? Exactly. Okay, because when you go to carbon, if you cannot make a decision based on what it is attached to, then you go to the next atom that it is attached to. In this case, this carbon is attached to a carbon, whereas this carbon here is only attached to hydrogen. So therefore, the ethyl has priority over the methyl. So this becomes B, and then of course this is C, and then this is D. Notice here, the group of lowest priority. What is the group of lowest priority? It's hydrogen. What is it doing? It's coming at you based on our Fisher projection. Remember a Fisher projection. The horizontal group is what? Remember what we told you earlier? Whenever you write the Fisher projection, the horizontal group is coming at you. Okay? The vertical group going away from you. So, let us make our motion here. I'm going to make my motion from A to B to C. Ignore group D. A to B to C. What kind of motion is that? It's clockwise motion, right? So that should be R, right? That should be R, is that correct? However, because we are breaking the rule, the group of lowest priority is coming at you instead of going away from you. This R, therefore, is going to be S. Okay, that is my rule. Okay? Because you only have two choices. You only have two choices, R or S. By the way, I published this about 20 years ago. This is what I'm telling you now. So, but your book is doing it differently. So you pay attention to what, you may want to follow your book, that is fine. Because your book tells you to rotate, to do this, to do that, no, that. Now, it's coming at you. Yeah. Yeah, it's horizontal in the Fisher projection. Exactly. So therefore, the absolute configuration of this molecule, therefore, of this carbon is actually S. Okay, you follow that. So therefore, I would therefore put S here. This is S. Okay. Then the enantiomer will be the opposite. Okay, but we could determine that also. Let us go ahead and do it. Okay, priority A. This is B. And this is C. And the hydrogen is D. Generally, you find that hydrogen is almost always going to be the last priority. Okay? Now let us make our motion. We make our motion from A to B to C. Ignore group D. So we go from A to B to C. And what is that motion? A counterclockwise motion, right? So we will expect that to be S. So, but the caveat is, but because the group of lowest priority is in the horizontal plane of the Fisher projection, which means that it is coming at you, then you switch. Okay? So this R actually should be, this S should be R. So therefore, the complete name of this compound, therefore, would be R paren 2-chlorobutane. Yes, go ahead. I can't hear you.
Oh, sorry. You're saying as a definition that if you have an R configuration, that the atom of each priority has to be going into the cube, or sorry, I'm going away from that.
No. We say that your motion, if your motion is clockwise, then that is R. If your motion is counterclockwise, that is S. However, if when you make that motion, the group of lowest priority is in the horizontal position of a Fisher projection, which means that it is coming at you. Then you got to switch. In other words, if you say this was R, then really it must be S.
So it's not a definition of either S or R?
No, that is not the definition. Okay. Okay. So the only definition of S or R is when it is clockwise is R, when it's counterclockwise is S. But keep in mind, if the structure you are, if the group of lowest priority is coming at you, then you must switch it. That is my rule. Okay. Okay. So anyway, so now we know how to name.
So you said it has to be something that both priority has to be coming at you.
No, it doesn't have to be coming at you. It depends on what the molecule looks like. Yes, if it's coming at you, you switch. Yes. If it's not coming at you, it's going away from you, you don't switch. Okay? So now we're giving you how to name enantiomers. We've also told you what enantiomers are. What are enantiomers? Exactly. Mirror images that do not superimpose on each other. Okay? These are stereoisomers. And we refer to them as chiral molecules. And we've also shown you how to name these chiral molecules, these enantiomers, by using the Kahn, Ingold, Krylov sequence nomenclature. Okay? What time do we have? Okay. We've got 2 more minutes. No, we've got 7 more minutes. I've got 2 minutes. And then 2 more minutes to talk, yes. So now, so what I advise you to do, I did post the lecture material in Blackboard. I would advise all of you to take a look at that lecture material in PowerPoint. A lot of the things that we've discussed so far today are there already. And then in addition to that, you could also watch the video of this, the webcast of this presentation today. When we come back on Tuesday, there is going to be a very short quiz on what we did today. Okay, so now I'm going to give you back your paper. So enjoy your weekend.